Anybody figure out where to start on this one? No. Problem might be a lot of people want to start off with 1 gram because that's what you do in Chem 1A. And then figure out stoichiometrically. We could do that, but it turns out that makes the problem harder, not necessarily easier. You know, this problem is really not that difficult if we know something, and that is if we know the solubility. For example, do you know the solubility of table salt? Solubility of table salt is 36 grams per 100 milliliters. That's a max. And so if you try to dissolve 37, well, 36 of the 37 will dissolve, 1 won't. If you wanted to dissolve 37, you just have to add a little bit more water. So if we wanted to dissolve 72 grams of table salt, how many milliliters of water would we have to add? Well, if 36 grams takes 100 milliliters, then 72 grams would take 200 milliliters, twice as much. And so if we know what the solubility is, then it's no problem. Well, we know how to calculate the solubility, right? Calculating solubility is just going left to right in the ice table. But this is not solubility in pure water, because the solubility calculations we did at the beginning were the solubility in pure water. This is solubility in ammonia. And so what impact will the ammonia have? Well, we have to take a look, because if we have, let's say, silver chloride solid, and then anything that deals with dissolving or precipitating it, we use the KSP equation. And so we'd like to call this step 1, but if you start trying to solve these stepwise, you're going to get into trouble as well. And so we have to rethink how we do these in this chapter. And so normally we could use an equation like this. We could calculate solubility in pure water. No ammonia around. The solubility in pure water, well, we can just look up the KSP value. Let's look up the KSP value for silver chloride here on the previous page. And so here it is. Silver chloride is 1.8 times 10 minus 10. It's not very soluble. Now this splits up into 2 ions, so the solubility would be the square root of that. And so the solubility is going to be about 10 to the minus 5 moles per liter. 10 to the minus 5 moles per liter comes out to like microgram per liter or something like that. You know, barely any of it dissolves. And so very little of this dissolves, but that's in pure water. In aqueous ammonia, what's going to happen? Well, what's going to happen is the Chalet's principle is going to take over. You know, because it turns out ammonia likes, does it like silver? This is ammonia like. And so we go over here and we take a look. You know, ammonia turns out to be a pretty good ligand to this base. And here we can see, yeah, ammonia likes silver. Ammonia likes a whole bunch of other ones too, like cadmium. Ammonia likes cadmium. Does ammonia like aluminum? It doesn't look that way, because if I look at the aluminum here, there's no amine complex here. But yeah, cadmium, cobalt, ammonia likes cobalt. Copper, we already saw that. Ammonia likes copper. Cobalt. Ammonia likes nickel. Does ammonia like lead? No. Ammonia likes platinum, though. Does ammonia like zinc? Yeah. How could you predict these things? Like, for example, ammonia doesn't really like lead. And so metathesis reaction would happen with lead, form lead hydroxide. However, you wouldn't form the complex with lead. How do you predict those things? Not only that, if you look at ammonia, sometimes ammonia, only 2 of those complex. Sometimes 4 of those complex. Sometimes 6 of those complex. How do you know? Is it going to be 2, 4, 6? How do you know? And so this is Lewis acid-base type reaction. What did we say about Lewis acid-base reactions? Are they easy to predict? No. The answer is you don't know. You don't worry about it. What you do is you look at what's been observed. You know, for example, why only 2 ammonias here on silver, whereas in copper it's 4, and in nickel it's 6? Well, why? I don't know. You know, we'd have to look into or we'd have to maybe have a better understanding of the theory, because the theory would be a more fundamental description of what's happening. Right? And so at this point, we don't really concern ourselves yet with why. I mean, we can figure out some of this stuff, but a lot of the stuff is beyond the scope of 1B. And so if we have a table like this, we just use it. And so it looks like ammonia does like silver. And so 2 ammonias will attack the silver. And how much does ammonia like silver? Actually quite a lot. Because if we go up here, it's 1.6 times 10 to the positive 7. So this is Kf. It's 1.6 times 10 to the positive 7. So what should we do? Should we do it stepwise? Put in 1 gram of silver chloride and then see where it leads? No, yeah, exactly. We can combine it, and that's exactly what we want to do. We want to combine it because of the. I'll tell you, ammonia is going to have a huge impact on the solubility. The reason ammonia has a huge impact on the solubility is because of this, Le Chatelier's principle. As the ammonia reacts with the silver, the free silver ion concentration goes down. If the silver ion concentration goes down, then this equilibrium has to shift to the right, and the solubility will go up. And so the best strategy here is to combine these two, silver chloride solid plus 2 ammonias. So it's the diamine plus chloride. What species is missing out of the combined? Silver ion, free silver. Is it reasonable to assume that the free silver ion concentration is very small, so the error that this introduces is small as well? Yes. It is if the first equilibrium, the K for the first equilibrium is small, that tells us that not much silver, free silver ion forms. Small. And then the second equilibrium, whatever free silver ion that does form is complex quite favorably, because the second K is large. So the combined method works here. The combined method works in chapter 17 because of this. It wouldn't have worked in any of the other chapters. So this is the only time we can use the combined method. And the combined method is great because, you know, if we tried to do this stepwise, we would have a hard time. You know, we'd have to do this simultaneous or something to figure out how to do this. I don't know. And so the combined method is quite handy for something like this. Now, that means we only have to do one ice table. If we only have to do one ice table, then it's not that bad. It's like a chapter 15 type problem. Silver chloride is a solid, and so we assume we have plenty of solid. This is the infinite solid. Well, we have 1 gram, and so we're going to assume that's enough. Actually, we want all 1 gram to dissolve. Now, what's the ammonia concentration? It's 15 molar. Do we have to do solution dilution here? Well, it depends. You know, when we dissolve a solid in a liquid solution, we usually assume the volume doesn't change much. That's different. If you take a gallon of water and add a gallon of water, you're going to have 2 gallons, but if we take a bunch of solid and dissolve it into a gallon of water, we're going to assume that we still have a gallon. And that's because the solute particles fit between the water molecules, and so it doesn't really expand the space too much. And so we don't do solution dilution here. It's, you know, liquid and solid, and this is going to be 0, and this is going to be 0. And so which direction are we going to go? Are we going to go left or are we going to go right here? Should we reset it? If we reset it, then we have to do that 1 gram. We have to convert that into moles and figure everything out. But I'll tell you, resetting is not the way to go here. Well, maybe it is. It depends on the K. Let's take a look at the K value. So the K for the combined is called KSPF. And it's just going to be the KSP times the KF. So let's see what that comes out to. KSP is 1.8 times 10 to the minus 10 times KF of 1.6 times 10 to the 7. Okay, we're going to write this in decimal form. 0.00288. And so when I look at the K, well, the K is smaller than 1, so it's more reactant than product. So maybe we should just leave it like this. You know, if the K was pretty big, then maybe we would think about resetting, but I'll tell you, when we do the combined, it's a little more tricky to reset because we have we got to reset it, considering the silver chloride. Normally we wouldn't. Normally we'd say, okay, we're going to reset this down to 0, but we can't reset it to 0 because we don't have an infinite amount of silver chloride. And so, if we did reset this and we had 1 gram of silver chloride, it turns out that 1 gram of silver chloride would be our limiting reagent. And that's going to set how much ammonia we have initially. And so, resetting can be done, but it's a little bit more tricky for the combined. Now, here, it's easy because here, it's got to go to the right. And so this is going to be minus. Now, when we go left to right, we call that solubility. And so this is going to be minus 2s plus s plus s. And so at equilibrium, I'm going to have 15 minus 2s, smaller, and s smaller. And so let's take a look at the KSPF expression. That's going to be the complex concentration times the chloride concentration divided by the ammonia concentration squared. And so the complex is S, the chloride is S, and the ammonia is 15 minus 2S squared. Now, I just automatically I just try the simplifying assumption. I don't think about it so much. If it works, great. If it doesn't, we didn't waste too much time. And so here, if I do the simplifying assumption, I'm going to assume that 2s is much smaller than 15. So we'll just get 15 squared on the bottom, and 2s drops out. Let's solve for S. So now the math is simple. And so different ways we could solve for S. I got S is equal to 0.8049. Right. Just check my calculation one more time. The square root of that. I'll take the square root of 0.0288. Times 15. Yeah, I get it. I solved it 2 different ways. I could get the same answer. 0.8049. Is that what you guys get? You got something different? 0.72 what?
0.7267. That's because I took the square root of both sides.
Okay, I took the square root of both sides. Maybe my calculators.
I got 0.729.
729?
Yeah, doing the square root.
All right, now let me take the square root of both sides. So I'm going to take the square root of 0.0288. 88. Oh, maybe I didn't put 2 8s on there. Times 15. I keep getting it. 0.8049. Well, anyway, we can always double check to see. And so let me just double check mine here. This is going to be 0.8049 molar, 0.8049 molar. And this would be equal to 15 minus 2 times 0.8049. Gives me 1.6099. Gives me 13.39. So let's see if these work out. So plugging these back into the K expression, I'm going to get 0.8049 squared. 0.8049 squared divided by 1.359 squared. Oh, not 1.3, divided by 13.39 squared. My numbers are off. When I double check it, I get a K equals 3.61 times 10 to the minus 3. In other words, I get a K of 0.00361. The K value should be 0.00288. And so I made a mistake here because, I mean, I wouldn't attribute this to round off. I'd attribute this to some calculation error. And so I made a calculation error. I got to find out where that calculation error is. And so this double check saved me the wrong answer here. And so what did you get, Juliana? 0.76.
I'm double checking.
Also could be because you get rid of the 2 in the simplifying assumption. I kept it.
Yeah, the 2s I'm going to get rid of in the simplifying assumption. Well,
What did you
actually,
keep?
maybe the simplifying assumption is not valid. You know, maybe I didn't have to do the simplifying assumption. I did the simplifying assumption. I forgot to check if it's valid by doing the percent change. The percent change is going to be the change, which is 2s over 15 times 100%. 2s, well, I just calculated over there, is 1.6099 over 15 times 100%. So let's see, 1.6099 divided by 15 times 100. I see. 10.7%. 10.7%, is that valid? No. That's why I'm so far off, because I used the simplifying assumption. The simplifying assumption wasn't valid. Well, that's not a problem because the math is actually quite easy, because you're right. We could just square root both sides. There's s squared on the top, we got a square on the bottom. If we square root both sides, we can figure it out. And so let's go ahead and solve for s without the simplifying assumption. So I'm going to get this. I'm going to get the square root of 0.00288 is equal to s over 15 minus 2s. All right, and so what is the square root of 0.00288? It's 0.0536. 65366 equal to s over 15 minus 2s. Okay, and then let's multiply by 15. Continue over here. Point 8049. Plus, or minus, sorry, minus 2 times s. 1073. I mean, 2 times 0.053 would be 1073s. 0.1073 s is equal to s. Let's add that to both sides. So we have 1.1073 s is equal to 0.8049. S is equal to 0.72688. Is that what you got? Okay. So let's try that instead here. So 0.7268, 0.7268. I'm not going to carry that many extra digits. Write them down there in case I need them for more exacting calculation. And so this is going to be 15 minus 2 times that, which is 1.453, which gives me 13.546 moles. All right, now let's double check this and see. And, so 0.7268 squared divided by 13.546 squared. So I get 0.02878, which is very close to 0.00288. This is probably within round off. If I carried more digits there, it'd probably be closer. It would be closer, for sure. All right, so we're good here. All right, so what did we just calculate? We calculated this, you know, all the silver chloride that dissolves, all the silver in the silver chloride that dissolves ends up here. And so for every mole of silver chloride that dissolves, I'm going to form 1 mole of the complex. And so in this case, I formed 0.7268 moles of the complex. That means all that came from this. And so what we can say is that the solubility is equal to 0.72688 moles of silver chloride for every liter. This is a 1-to-1 mole ratio. So for every 0.72688 moles of silver chloride that dissolves, all that silver is going to go into the diamine complex, so I'll get the same 0.72688 moles of that. So this is what we call the solubility. It's a solubility of silver chloride, and it's related to these concentrations here. Now, if I know what the solubility is, then I can easily calculate how much solution I need. So here I have 1 gram of silver chloride. Silver is 107 point, molar mass, 107.87. I'm going to round it. Molar mass is typically rounded. Chlorine's 35.45. It's 12, 13. 143.32. 143.32 grams per mole. And so this gives us moles of silver chloride. Well, for every mole of silver chloride, or for every 0.72688 moles of silver chloride, I'll have a liter of solution. Well, where did that solution come from? The solution came from the ammonia. That's it. So let's calculate this. It's 1 divided by 143.32 divided by 0.72688. 9.599 times 10 to the minus 3 liters of solution. This gives me 9.59 of 9 milliliters of 15 molar ammonium. So all the solution came from the 15 molar ammonium. And so we need 16, not 16, we need about 9.6 milliliters. That should dissolve a gram of silver chloride. So this is KSPF. And KSPF, we're primarily interested in the solubility. How is the solubility going to be impacted by the formation of a complex? And the answer is it's going to be significantly impacted because formations are very favorable. Look at all these powers here, 10 to the 33. The smallest one is quite large, 10 squared, it's pretty big. All right, so that's the strategy. In fact, it's just Le Chatelier's principle in action. So let's revisit the acids. Revisit solubility and pH. If we revisit solubility and pH, then we're going to introduce something called KSPA, A for acid. This is a slightly different equation than KSPF. So let's take a look at KSPA right now. For example, barium hydroxide. Is barium hydroxide very soluble in water? So let's take a look at the KSP for barium hydroxide and see. Here's barium hydroxide, 5 times 10 to the minus 3. And it's not that soluble in water, somewhat soluble. Its KSP is kind of on the larger side. And that's because hydroxides are all insoluble except for group 1 ammonium and calcium, strontium, barium. And so normally we consider barium hydroxide as soluble. But what is this? More soluble in water, more soluble in base, or more soluble in acid? In acid. This is going to be much more soluble in acid. And why? Because acid is going to have very little hydroxide. The less hydroxide we have, the more this equilibrium shifts to the right. So the lower hydroxide, the more it shifts to the right, and the better off we are as far as solubility if you want to dissolve it. And so this is what we saw earlier. This is a direct or somewhat direct effect of pH or POH on there. But the next example we're going to look at is something like barium carbonate. Is barium carbonate very soluble? Well, carbonates are all insoluble, except for group 1 and ammonium. Barium carbonate is no exception. If we look at barium carbonate is 5.1 times 10 minus 9. It's not very soluble. Oh. And so we can calculate the solubility in pure water. we calculated solubility in pure water, we just use this, the ice table here, and then we shift it to the right. When we shift it to the right, that's the solubility. KSP 5.1 times 10 minus 9, so not very soluble in water. However, we can make it less soluble by, for example, if we want to make it less soluble, we want to precipitate something, we'll just add common ion. So if I'm trying to precipitate out carbonate, I'd add more barium. If I'm trying to precipitate out barium, I'd add more carbonate. I'll shift it to the left. We can also try to make it more soluble. How can we make it more soluble? The way we can make it more soluble is by shifting it to the right. How can we shift it to the right? Well, as we saw in the previous examples, if we can form a complex, we can shift it to the right. And so does barium ion form a complex with a ligand? Let's take a look. And so can you predict it? Well, it's hard to predict. So we just consult appendix D. We look, does barium form a complex with a ligand? So look here. No. Well, barium doesn't form a complex. This is alphabetical according to, so we jump from A to C. So I don't see barium there. If I look at silver, silver does form complexes. Silver likes to form complexes. For example, here, we have all these complexes of silver. Let's go back to this other KF chart here because it's a little simpler. So what complexes? I don't know. We look it up on the table. What complexes form for silver? And so when I look it up on the table, I see 3 on this table. It'll complex of ammonia, cyanide, and thiosulfate. Out of these 3, which one is most favorable? Ammonia, cyanide, or thiosulfate? Cyanide. Cyanide is the most favorable. Look at it. Cyanide's 10 to 18. Cyanide's the best. Cyanide would be the best complexing agent, but there's a problem with cyanide. The problem with cyanide is it's so toxic. So we don't want to use cyanide, even though it's the best. So let's use the next best. So what's the next best? The next best would be thiosulfate. It's 10 to the 13. But did you see much thiosulfate in the lab? No, we don't have that much thiosulfate because thiosulfate is it's a pretty good Lewis base like this for certain metals. Not zinc, if you see, but for silver, yeah. But the problem is thiosulfate is also a good reducing agent. And therefore, it's prone to oxidation. It's prone to decomposing, so you have to protect it. Otherwise, the thiosulfate can decompose. So it's a hassle. It's not stable over a period of time. Because the thiosulfate's a hassle because we need fresh thiosulfate, otherwise it might decompose or have decomposed. So that brings us to ammonia. Ammonia is the worst of the 3. But the good thing about ammonia is it's plentiful. We have plenty of ammonia in lab. It's cheap, and so we can use ammonia. And so we use ammonia, and ammonia is no slouch because it's 10 to the 7. 10 to the 7 is actually quite large. And so we look for something that can complex barium. If we find something that can complex barium, then we can shift this to the right and really kick up its solubility. But we don't have anything that complexes with barium. Maybe carbonate can act as a Lewis base. And here, we don't know. We can check appendix D and C. Is carbonate a decent ligand? Do you see any carbonato complexes? When you scan the table, do you see anything with carbonate? No. So you know what? We got to give up. No KSPF. There's no KSPF for this because we can't form any kind of complex with either barium or carbonate. But we do have another possibility, and that's a KSPA. What do you know about carbonate? Well, carbonate's a proton acceptor. And so carbonate is a base Well, if carbonate's a base, then we have an acid here, hydronium. And so we can see what happens here. Hydronium and carbonate is going to form bicarbonate and water. Well, what's the K for this reaction? The K for this reaction I've been trying to tell you guys. If we take a strong acid like hydronium and a weak base like carbonate, then is it very large, very, very large, or very, very, very large? A strong acid plus a weak base like carbonate is very, 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 or very, 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 very large. Well, that's chapter 17. For chapter 18, we don't do that. For chapter 18, we want an actual number for this. How can we get a number? The way we can get a number is by looking at this backwards. If we look at this going backwards, what is this? Going backwards, this is hydrolysis. Is this acid hydrolysis or base hydrolysis? This is acid hydrolysis. Bicarbonate plus water forms hydronium and carbonate. And so that's the K for this is actually 1 over Ka for bicarbonate. Well, the Ka for bicarbonate we can find in Appendix D or in the chapter. Let's just get it off Appendix D here, since I'm at Appendix D. The Ka for bicarbonate is 4.7 times 10 minus 11. And so the K for the second one is 1 over 4.7 times 10 minus 11. Now I have two equilibria. And the first one is small. The second one is large. And so what you know what this is? This is combined. We can combine these two and we get barium carbonate plus hydronium is going to give us barium 2 plus bicarbonate plus water. This is what we call KSPA, but the A is not multiplied directly. It's actually 1 over Ka. And so KSPA is equal to KSP divided by Ka for bicarbonate. And so what we can do is we can do this as one ice table rather than trying to do this simultaneous or stepwise or whatever else. We just have one ice table to solve here. And so the exact same situation comes up. You know, how much 6 molar HCl do I need to dissolve 1 gram of barium carbonate? Exact same problem that we just did. We just calculate the solubility of barium carbonate in 6 molar HCl, and then we're done. We could use HCl to dissolve our barium carbonate, and we could use a complex formation to dissolve our silver chloride, but both of them are exactly the same. It's a Le Chatelier shift on the KSP equation to the right. Okay, it's just looking for different things that react. All right, I'll stop here, and then actually that's pretty much it for chapter 18.